Welcome to Curiosity, the podcast where science meets wonder. Join us as we explore the fascinating, the innovative, and the unexpected, from the secrets of the cosmos to the marvels of everyday life. Each episode takes you on a journey to uncover the knowledge and stories that fuel our endless quest for understanding. Let your curiosity guide you.
I want to start today's exploration with a bit of a visualization experiment.
Okay, I'm game.
So wherever you are, and unless you are currently operating heavy machinery or merging onto a highway, I want you to close your eyes.
Safety first, please.
Absolutely. But if you're safe, just close them for a moment. Now, I want you to picture yourself, high above the earth. Maybe you're in a plane, or maybe you're just floating there like a superhero, and you're looking down at a coastline. Pick a rugged one.
Like Norway.
Norway is perfect. Or the Pacific Northwest. You see those jagged edges where the land just crashes into the sea?
Yeah.
Huge bays, rocky peninsulas jutting out. You got it.
I'm there. It's windy.
Okay. Now imagine you have a camera with like a magical infinite zoom lens.
Yeah.
I want you to zoom in on just one of those big rocky peninsulas. As you get closer, what do you see?
Well, the closer I get, I start to see that the big peninsula isn't smooth at all. It has its own little bays, its own smaller rocky points jutting out.
Right. It looks remarkably similar to the big picture, just smaller.
Yeah.
Now zoom in again. Pick one of those smaller rocky points.
Right.
Closer. Now you're basically standing on the beach. You're looking at a single boulder.
And then it's rugged. It's got, cracks, bumps.
Zoom in again. Look at a tiny pebble on that boulder.
Okay.
Zoom in one more time. Look at a grain of sand under a microscope.
And the pattern just, it holds. It's still rough. It's still jagged, still complex.
And that is the hook for today. If you did this with a man-made object, say a plastic ball, eventually you'd hit a smooth surface.
Yeah.
But with nature, as you zoom in, the complexity just doesn't go away. It repeats.
What you're describing right there is the fundamental difference between the world we build and the world nature builds. And it brings us to the central mystery we're unpacking today.
Which is why?
Why does nature, which we usually describe as messy or chaotic or wild, actually look the same at different scales?
It turns out it's not messy at all. It's following a hidden rule book, a kind of hidden geometry. Today, we are talking about fractals.
Fractals. This is one of those topics that once you really get it, and I mean really wrap your head around it, you will never, ever look at a tree or a cloud the same way again.
It really does rewire your vision, doesn't it?
Completely.
And we are going to go everywhere with this today. We're going to talk about trees, sure. That's the obvious one. But we're also going to talk about the blood vessels inside your own body, the structure of the entire universe.
And even why it's impossible to truly measure the length of a coastline.
Oh, that one is going to hurt some brains.
For
It
sure.
hurt mine. But before we get to the brain-hurting stuff, we have to define this properly. Because fractal is a word people throw around a lot, like quantum or organic. But what does it actually mean? The material we're looking at uses this term self-similarity.
Right, and that is the absolute core concept. Self-similarity means, pretty much literally, that a part of the whole looks like the whole thing.
Okay, but let's contrast that with what we're used to. Because I remember geometry class. I remember Mr. Henderson making us draw squares and circles and triangles.
Euclidean geometry, the classics.
Right. And everything was smooth. A circle is a perfectly smooth curve. A triangle has perfectly straight lines.
And that's the problem, really. For thousands of years, we tried to use those perfect shapes to describe nature. We'd say, oh, the Earth is a sphere, or a tree trunk is a cylinder.
But it's not, is it?
Not even close. If you actually look at a tree trunk, it's rough, it's textured, it's bumpy. Nature isn't smooth. Clouds are not spheres. Mountains are not cones. And lightning definitely does not travel in a straight line.
So for a long time, scientists just thought nature was, bad at math.
In a way, yeah. They treated all that roughness as error, as just, messiness that got in the way of the pure geometric shapes they had in their heads.
But it's not an error.
Exactly.
Yeah.
In the last few decades, we realized that the roughness isn't an error at all. The roughness is the geometry.
And that's where the fractal comes in.
That's it. A fractal is a shape that keeps its complexity forever. There are really three things you need to remember. 1, infinite complexity.
Meaning you never run out of detail, no matter how much you zoom.
Right. 2, self-similarity.
The small piece looks like the big piece.
And 3, iterative process.
Iterative. That means repetition.
Yes. And this is the secret sauce. This is the big reveal. Complex shapes in nature aren't built from a complicated blueprint. They are built from a simple rule repeated over and over and over again.
I love that idea, that all this complexity, the incredible beauty of a forest or a storm, it all comes from simplicity.
Just a simple rule on a loop, a feedback loop.
So, okay, let's get out of the abstract and look at the real world, because once you know what to look for, these things are, well, they're literally everywhere. The sources start with the most obvious one, plants, specifically trees.
The tree is the prototype. It is the classic fractal.
I was looking at the oak tree in my backyard this morning trying to see the math, and it's actually pretty intuitive once you start breaking it down. You have the trunk. That's your starting point.
Level 1. The trunk grows up.
And then it splits.
Right. That's the rule. It's an algorithm. Grow X amount, then split into 2 branches. That's the first iteration of the rule.
Then you look at those 2 main branches. They grow for a bit, and then they split again.
Second iteration.
And then those smaller branches split into twigs, and then the twigs split into the veins on a leaf.
It just keeps going. And if you were to, say, cut off a branch, don't actually do this, be nice to your trees.
Right.
But if you did, and you stuck it in the ground, it looks just like a miniature tree. The part resembles the whole.
But here's the question I kept asking myself while I was reading this. Why? Why does a tree do this? Is it just trying to look cool for us?
Nature is rarely vain. It's almost always pragmatic. Form follows function. So think about the job of a tree. What is a tree trying to accomplish?
Well, stay alive.
Sure, but how does it do that?
Photosynthesis. It needs sunlight.
Exactly. It needs to capture as many photons as possible. Now imagine if a tree was just a big flat sheet like a billboard. It would catch sunlight, sure, but it would also catch wind like a sail and probably blow over in the first big storm. Plus, the top leaves would block all the bottom leaves completely.
It's not a very efficient design.
It's terrible engineering. But by branching out fractally, the tree maximizes its ability to spread its leaves across a 3-dimensional space.
So it can get light from all angles.
It can capture light from above, from the side, from an angle. It minimizes what's called self-shadowing.
So it's all about surface area then?
It's about maximizing surface area while minimizing the cost. And wood is expensive, biologically speaking. It takes a ton of energy to grow a trunk. The fractal branching allows the tree to support the maximum number of leaves with the minimum amount of structural wood.
It's an optimization algorithm written in bark and leaves.
It is biological engineering at its absolute finest. And it's not just about sunlight either. Think about what's happening underground, the roots.
Oh, right. They're doing the exact same thing.
The exact same thing, just looking for water and nutrients instead of light.
Because if the roots were just one big tube going straight down, they'd miss all the water in the surrounding soil.
Exactly. By branching, they explore the entire volume of the soil. They touch every cubic inch of dirt to suck up what they need.
So the tree is basically this explosion of surface area in 2 directions, up for light, down for water.
And the most efficient possible shape for that explosion is a fractal.
We have to mention ferns here, too. The notes say that ferns are basically prehistoric.
Oh, ferns are ancient. They've been around since way before the dinosaurs. And they are, visually, maybe the most obvious fractal you can find.
Yeah, they are.
If you look at a fern frond, it's made up of all those smaller leaflets.
Right.
Now look closely at just one of those leaflets. It is shaped exactly like the entire frond. It's a perfect copy, just scaled down.
And then the leaflet itself is made of even smaller sub-leaflets that look the same.
All the way down. The fact that this design is hundreds of millions of years old tells us something really important.
That it works.
It tells us that this isn't a fad. This is a fundamental solution to the problem of life on Earth. Nature stumbled upon this repeat the pattern trick very, very early on and said, yep, this one's a keeper.
Speaking of things that look like they were designed by a mathematician.
Yeah.
Have you ever really looked at Romanesco broccoli?
The chartreuse vegetable that looks like it belongs in an alien invasion movie?
Yes. That stuff freaks me out a little bit. It's too perfect.
It is absolutely stunning. It's my favorite example to show people because you don't need a microscope or anything. You just need to go to the grocery store.
It's those spiraling cones.
Right. The whole head is a big cone made of spirals. But then you look at one of the individual spirals, and it's a cone made of even smaller spirals.
And if you break off a piece?
A fleuret. It looks exactly like the whole head.
These fractals all the way down.
It really is.
Yeah.
And it's also following the Fibonacci sequence, which is a whole other mathematical rabbit hole we could go down. But the point is, That vegetable is built by a simple mathematical rule repeated at every single scale. It's physical proof that math underlies biology.
Okay, so we've got trees, ferns, alien broccoli. That's the visible world around us. But this is where the research took a turn that I really wasn't expecting. And honestly, it's where I started to feel a little observed. Because we aren't just looking at fractals.
We're fractals.
We are talking bundles of fractal geometry. If you could see inside your own body, you'd see the exact same patterns we just described in the forest.
Let's start with the circulatory system, the blood.
Okay, think about the logistical nightmare of the human body. You have, roughly 37 trillion cells?
37 trillion. That's an insane number.
And every single one of them needs a constant delivery of oxygen and nutrients and a constant pickup of waste. If any cell is cut off, even for a short time, it dies.
And you've only got one pump, the heart. One pump. So how do you connect that one pump to 37 trillion individual destinations?
Well, if you just ran a separate tube to every cell, you'd be bigger than a stadium. It's impossible.
Absolutely impossible. So the body uses the fractal branching method. The aorta is the trunk of the tree.
It's huge.
Then it splits into major arteries. Those split into smaller arteries. Then arterioles. Then finally, capillaries.
I mean, capillaries are tiny.
They are microscopic, but the network is so dense, so incredibly efficient, that no cell in your body is more than a hair's breadth away from a blood vessel.
Wow.
The fractal structure allows the blood system to fill the entire volume of your body without being your entire body. It leaves room for, muscles and bones and organs.
That is just incredibly clever. But the example that really messed with my head in a good way was the lungs, what the source called the respiratory paradox.
Yes, this is a classic problem in biology, a beautiful one.
So lay it out for us. What is the paradox?
The paradox is all about surface area versus volume. To stay alive, you need to get oxygen from the air into your blood. That exchange happens across a membrane, a surface.
Okay.
Now, humans are big, active animals. We burn a lot of energy, so we need a massive amount of oxygen. And to get that much oxygen, you need a huge surface area for the exchange to happen on.
How huge are we talking?
If you could take the total surface area inside your lungs and somehow iron it out flat, it would be roughly the size of a tennis court.
A tennis court?
A tennis court.
Wait, inside my chest?
Right now.
Yes. Look at your chest. It is not the size of a tennis court. It's a pretty small box.
Yeah.
So the engineering problem for evolution was, how do you fit a tennis court into a shoebox?
If I tried to stuff a tennis court tarp into a shoebox, I'd just have a crumpled mess.
And that is exactly what your lungs are. They're a controlled mathematical crumple.
A controlled crumple, I like that. It starts with the trachea, the windpipe, that's the trunk. It splits into two bronchi, those split into bronchioles, and they just keep splitting and splitting maybe 23 times, getting smaller and smaller.
Until they end in the alveoli.
The 300 million tiny air sacs called alveoli, that branching structure is the only way to pack that much surface area into that little volume.
So if our lungs were just simple bags like balloons,
the surface area would be tiny, we'd suffocate in minutes. We literally owe our lives to fractal geometry.
It's just so interesting to think that evolution just found this solution.
And it found it over and over again. Fish gills, they're fractal. Bird lungs, also fractal. Even the placenta that nourishes a fetus is a fractal structure. Evolution is a ruthless editor. It throws away what doesn't work. And it kept this design because it is mathematically the most efficient way to exchange energy.
And it's not just the lungs, though. The brain does this too, right?
The brain is arguably the most complex object in the known universe. And yes, it relies on fractals in a couple of ways. First, the neurons themselves, the brain cells.
They look like little trees.
They do. In fact, biologists call them dendritic trees.
Dendritic.
Yeah.
That comes from the Greek for tree, doesn't it?
It does. They branch out to connect to other neurons. One single neuron can have thousands of connections precisely because of that branching structure. It creates this web of immense complexity.
And then there's the look of the brain itself. The wrinkles. The walnut look.
The folds. And it's the exact same logic as the lungs. You want processing power. Processing power happens in the cerebral cortex, the outer layer of the brain. So you want as much of that layer as possible. But you have a skull limitation.
You can't just grow a giant head. It wouldn't fit through the birth canal, for one thing.
Exactly. So nature folds the brain. It crinkles it up. The ridges and valleys, the gyri and sulci, allow you to pack a massive amount of brain surface area into a helmet-sized skull.
So if your brain were smooth,
you'd be significantly less intelligent.
So being smooth-brained is literally an insult to one's geometry.
It is scientifically accurate shade, yes.
Okay, so We've zoomed into the cells. We've seen the lungs, the blood, the brain. Now I want to do the opposite. I want to pull way, way back. Let's talk about the massive scale. Geology.
Yeah.
The planet itself.
This brings us right back to our coastline visualization from the start.
And mountains, too.
Think about a mountain range. From a satellite, it looks like wrinkled rock. If you land a helicopter on a single peak, the rocks around you look like wrinkled rock.
And if you pick up a stone.
It's wrinkled rock. It's self-similar, and this is caused by erosion.
Water and wind.
Water, wind, gravity. These forces don't care how big the object is. Water flows downhill, whether it's a tiny trickle on a crack or a massive river carving a canyon. The physics are the same at every scale, so the shapes they carve are self-similar.
Speaking of rivers, we talked about blood vessels being the rivers of the body. Well, rivers are the blood vessels of the earth.
It is the exact same branching logic, just with water instead of blood. The Mississippi River Basin is a colossal fractal. You have these huge tributaries feeding the main river, smaller streams feeding those, tiny creeks feeding those.
And it's all about optimization.
Yes. It optimizes drainage. Gravity wants to move water from the high ground to the ocean with the least amount of resistance. The fractal network is the path of least resistance. It drains an entire continent with maximum efficiency.
Okay, now, we have to talk about the coastline again.
Yeah.
Because in the notes, there's a section on something called the coastline paradox, and there's a name attached to it, Benoit Mandelbrot.
The father of fractal geometry, he's the one who really coined the term back in the 1970s and brought all these ideas together.
So this paradox actually kind of annoyed me when I first read it, because it sounds like nonsense. The concept is, the length of a coastline depends on the ruler you use.
It sounds impossible, right? A physical object should have a fixed, measurable length.
Right. If I measure my desk, it's 5 feet wide. If I use a yardstick, it's 5 feet. If I use a tape measure, it's 5 feet. The length doesn't change.
But a desk is smooth. A coastline is fractal. Let's walk through the thought experiment Mandelbrot used. Imagine you are measuring the coast of Great Britain, and you have a giant ruler that is, say, 100 kilometers long.
That is a very big ruler.
Just go with it. You walk this ruler around the perimeter of the island, you lay it down end to end, because the ruler is so big and straight, it just bridges over massive bays, it cuts across inlets, it ignores all the wiggly bits.
Okay, so I get a number.
Yeah.
Let's say 2,000 kilometers.
Fine. Now, you throw that ruler away, and you get a 1-kilometer ruler.
A much more manageable size.
Now, you can't just bridge over the big bays. You have to walk your little ruler into the bay and back out. You have to trace the ins and outs of the headlands more closely.
So my path gets longer, the measurement goes up?
Much longer. You're adding all those extra detours.
Right.
Now, swap again. Use a standard 12-inch school ruler.
Whoa.
Now you have to measure around every single boulder on the beach.
The length is going to explode.
Now, use a micrometer. You are measuring around every pebble.
Okay, I see where this is going.
Now you measure around every grain of sand. Now you measure around the atoms in the grain of sand.
So does the measurement ever stop increasing?
Theoretically, no. As your measuring stick gets smaller and smaller, the measured length of the coastline approaches infinity.
Wait, pause. You're telling me that the coast of Great Britain, an island you can drive across in a day, has a technically infinite perimeter?
It has an infinite perimeter contained within a finite space. That was Mandelbrot's breakthrough. He realized that these rough, fractal shapes don't play by the rules of standard geometry. They are infinitely complex.
That is deeply unsettling. It basically breaks the whole concept of measurement.
It forces us to admit that measurement is, in some ways, subjective. It depends on the observer. It depends on your zoom level. To a giant in space, the coast is smooth and short. To an ant on the beach, it's jagged and incredibly long.
So reality depends on how big you are.
In a fractal universe.
Yeah, kind of.
Okay, let's look up for a second. The sky, clouds.
Ah, clouds. The bane of early computer animator.
Why? Because they're fluffy. Because they are fractals. A cloud isn't a sphere. It isn't some simple shape you can just program. It's a puff made of smaller puffs, which are themselves made of smaller puffs. If you try to model a cloud using simple spheres, it just looks like a bunch of ping pong balls glued together. It looks fake.
So to make it look real,
You have to use fractal math. You have to tell the computer to repeat a puff pattern at smaller and smaller scales.
and what about lightning?
Lightning is the electrical version of the river system. It's trying to find the path of least resistance through the air to the ground. And the air isn't uniform. It has pockets of dust, temperature changes, humidity, so the main bolt branches. Then those branches branch. It's searching for the ground in a fractal pattern.
The source also mentions weather prediction here, the famous butterfly effect.
This is so crucial. Because weather is a fractal system, the scales are all connected. In a simple, smooth system, a tiny change here stays tiny over there. But in a fractal system, a small detail at a microscopic scale can cascade upwards.
A butterfly flaps its wings in Brazil.
And causes a tornado in Texas 2 weeks later. It's a bit of an exaggeration, but the principle is sound. Because the atmosphere is a connected fractal system, you can't ignore the small stuff. The small stuff feeds the big stuff. And that's why we can't predict the weather perfectly beyond a few days. The complexity is literally infinite.
And finally, the ultimate zoom out. The cosmos.
The cosmic web.
I'm talking about the arrangement of galaxies.
Exactly. When astronomers started mapping the universe in 3D, I think they expected to see stars spread out more or less evenly, like butter on bread.
Smooth. Uniform.
But that's not what they found at all. They found clustering. Galaxies cluster into groups. Those groups cluster into superclusters. And these superclusters form these massive filaments, these glowing strands of light stretching across the dark.
And in between them,
giant voids, just empty space. The universe looks like a sponge or a spider web. And the crazy thing is, it looks self-similar. Whether you look at a relatively small patch of the sky or a massive chunk of the observable universe, the pattern of clustering looks about the same.
So gravity itself shapes matter fractally.
On the grandest scale we can imagine, yes.
Okay, so we've seen the what. We've seen the trees, the lungs, the coastlines, the galaxies. Now I want to get into the how, the mechanism. We touched on the math with Mandelbrot, but the source mentions something called fractal dimension, and it calls it a mind-bending concept.
It is abstract, but I think we can crack it. It's not as scary as it sounds.
Okay, help me out here.
In school, we learn integer dimensions. A line is 1D. A flat piece of paper is 2D. A solid cube is 3D.
Got it. 1, 2, 3. Simple enough.
But where does a coastline fit in? It's a line, right? So you'd think it's one-dimensional.
Sure.
But it's so jagged, so crinkly, so wiggly that it starts to fill up space. It starts to act like it's trying to be a surface, a 2D object.
It's a very ambitious line.
Exactly. It's more than a simple line, but it's not quite a full shape. So mathematically, it has a dimension somewhere in between 1 and 2. A typical coastline might have a dimension of, say, 1.3.
1.3 dimensions. That just sounds like a glitch in the matrix.
Think of that crumpled paper ball we talked about earlier.
Right.
Take a flat sheet of paper, that's 2D, now crumple it up into a tight ball.
Right.
It's now acting like a 3D object. It has volume, you can throw it across the room. But if you were to uncrumple it, it's still just a 2D sheet of paper. While it's crumpled, it's existing in a fractal dimension. It's maximizing its presence in 3D space while remaining fundamentally 2D material.
That is actually a really helpful visual. So my lungs are a 2D sheet of tissue that's acting like a 3D organ.
Precisely. They have a fractal dimension of roughly 2.7. They are almost solid, but not quite. That's what allows for all the empty space for air.
That explains the what of the math. But I want to get to the why of the biology. The source has a section here called genetic economy, or the lazy gene theory. And I felt like a light bulb turned on when I read this.
This is my favorite part of the whole thing. It explains how complex life is even possible.
So think about DNA. It's code.
Yeah.
It's a set of instructions.
Right. It's a blueprint. But DNA is microscopic. There is a very limited amount of storage space in the nucleus of a cell.
Okay. So if you wanted to build a tree.
If nature built a tree the way an architect builds a skyscraper, the DNA would have to specify every single part. Twig number 4005 goes left at a 30-degree angle. Twig number 4006 goes right at a 32-degree angle.
You need a unique line of code for every single leaf.
The DNA would have to be miles long. It's too much data. It's completely inefficient. It's like trying to save a photo on your computer by describing the color of every single pixel individually. The file size would be enormous.
So how does nature solve this problem?
Compression. Nature uses an algorithm. Instead of specifying every twig, the DNA just has a very simple instruction. Here's the rule. Grow 5 inches, split it 40 degrees, and then just repeat.
That's it.
That's it. You write that simple code once, you tell the organism to repeat it 10,000 times, and boom, you get a complex, beautiful, massive tree.
It's like a zip file for biology.
It is exactly like a zip file. A zip file works by finding patterns in the data and creating a shorthand for them. Nature is the ultimate compressor, and that's why a tiny little acorn can hold all the instructions for a giant redwood tree. It doesn't hold the picture of the redwood, it holds the formula to generate the redwood.
That is incredibly elegant. It means complexity is basically free.
Complexity is cheap if you use fractals. You get infinite detail for very little coding effort. And that is why fractals are everywhere in nature. Nature is lazy, or rather, it's ruthlessly efficient. It found a way to get the maximum possible result for the minimum possible effort.
This reminds me of video games. I read somewhere that in early games, artists used to have to hand draw every single tree, and it took up huge amounts of memory.
Right, but modern games use something called procedural generation. They just have a line of code that says, make a fractal tree here, and the computer grows it on the spot. It saves a ton of memory. We are literally using nature's ancient trick to build our virtual worlds.
Which brings us perfectly to our final section, human applications. Biomimicry. We're just copying nature's homework.
We are, and we're getting much better at it.
The source mentions antennas. And this is a story I had never heard before.
It's a great story. Think about old cell phones, or even old TVs. They had those long, straight antennas, rabbit ears.
I remember having to pull the antenna out of my old flip phone to get a signal.
And a straight wire is only really good at picking up one specific wavelength of signal. If the signal's wavelength matches the wire's length, great. You get a clear signal. If not, you get static.
But our modern phones have to pick up everything.
Yeah.
Bluetooth, Wi-Fi, GPS, 4G, 5G. Those are all completely different wavelengths.
So you'd need 10 different antennas sticking out of your phone. It would look like a porcupine.
Not a great design.
So back in the 90s, an engineer named Nathan Cohen thought, what if I bend the wire? He bent a wire into a specific fractal shape. I think it was a shape called the Cox snowflake.
Like the coastline? Jagged?
Exactly. Because the fractal wire has big bends, medium bends, and tiny little bends all on the same wire, it can receive big wavelengths, medium wavelengths, and tiny wavelengths all at the same time.
It's a multi-band antenna.
And because it's folded up on itself like the lungs, it fits onto a tiny little chip inside your phone.
So the reason my iPhone has no antenna sticking out is because there is a tiny hidden fractal inside it.
You are carrying a piece of applied fractal geometry in your pocket right now.
That is wild. The notes also mention cities.
This is less intentional, but it's still true. We don't usually plan our cities with fractals in mind, but they tend to grow that way anyway.
Just organic growth.
Exactly. Look at a map of an old city like London or Tokyo. You have the city center, then major arteries leading out, then smaller neighborhood streets, then tiny alleys. It follows the same branching pattern as blood vessels.
Or the internet.
The internet topology is a massive fractal web. It's the most efficient way to connect millions and millions of points. It seems like whenever a network needs to grow and distribute things, whether it's data, cars, blood, or sap, it naturally falls into this pattern.
We can't escape the geometry. Even when we think we're building our own things, we just end up mimicking nature.
Because the mathematics of efficiency is universal. It's the same for a tree as it is for a data network.
So what does this all mean? We've covered a lot of ground today. We've gone from the beach to the galaxy, from our lungs to our iPhones. For me, the biggest takeaway is this huge shift in perspective.
It's a paradigm shift, really.
I used to look at a forest and think, that's chaos. It's pretty, but it's a mess. And I'd look at a skyscraper and think, now that's order.
And this whole idea just flips that on its head.
Completely. Nature isn't messy. It's just using a different kind of geometry, a geometry of growth, a geometry of roughness.
And I think it connects us to the world in a really profound way. It's so easy to feel separate from nature. We live in our square boxes. We look at our flat screens. But when you realize that the branching of the veins in your own hand follows the exact same math as the branching of a river or a lightning bolt or a tree, you realize you aren't just in the universe.
You of the universe.
We are built by the same code. We are echoes of the same fundamental equation playing out at different scales.
So as we wrap up, I want to leave our listeners with a final thought to mull over.
I'd say this. Fractals suggest that the universe isn't arbitrary. I think we often fear that things are just random chaos, that there's no rhyme or reason to it all. But fractals show us that there is a deep, elegant logic underlying creation. There's a pattern that repeats from the atom all the way up to the star. There is order in the roughness.
Order in the roughness. I like that a lot. And here's my challenge to you, the listener. Don't just let this be an interesting thing you listen to today. Take it outside.
Yes. Go look at a cloud.
Look at a tree. Look at the palm of your hand. Don't just look at it. Look for the pattern. Try to see the self-similarity. Try to see the branching.
Because once you turn that switch on in your brain, you can't turn it off. You will see it everywhere.
And it might just make the world feel a little bit more magical and a little bit more logical all at once. Thanks for joining us on this journey into the hidden geometry of nature.
It was a pleasure.
See you next time.